The oscilloscope is a versatile electronic test instrument. The purpose of the oscilloscope is to visually display voltage over a time period at different points in the circuit. Ensure that any electrical equipment in the labs have green safety labels. The oscilloscope is connected to the circuit using a probe lead. The probe lead is connected to one of the BNC sockets on the front of the oscilloscope. Switch the oscilloscope on and wait for 5 to 6 seconds. Then press any key to enter the active mode. Adjust the screen intensity using the backlight dial so that the trace is sharp and clear to allow accurate readings to be taken. The front panel of the oscilloscope contains a display screen and all the controls required to display the electrical signal on the screen. By adjusting the controls, the waveform can be displayed conveniently on the screen for measurements to be taken. The two main sets of controls are for the Timebase and Y amplifier settings. Most oscilloscopes can display two traces at any one time using two channels, and each channel has its own set of Y amplifier controls. The Timebase controls are common to both Y amplifier channels. It is important to note that adjusting the front panel controls does not change the measurement. It only affects the trace on the screen in a way that ensures a convenient display. The screen of an oscilloscope is used to display the voltage being measured. On the screen is a grid arrangement that can be used to take readings. Time is measured over the horizontal axis, while voltage is measured vertically. The grid is typically 10 by 8 divisions. The quantity that each division represents can be set using the Timebase and Y amplifier controls. For example, if the Y amplifier is set to 2 volts per division, then each division vertically represents 2 volts. The grid division is marked with 5 additional divisions, allowing readings to be taken with greater accuracy. The Timebase is measured in seconds, with the Timebase control typically providing values in milliseconds and microseconds. The value represented by each vertical division can be adjusted using the Y amplifier control. The Y amplifier is measured in volts, with the Y amplifier typically providing values in volts and millivolts. When a trace is displayed on the screen, it may be more convenient to take an accurate reading if the trace is moved to align with the grid lines. The X position control allows for the horizontal alignment of the trace, while the Y position sets the vertical alignment. A separate Y position control is available for each channel. It is important to remember that adjusting these controls does not change the measurement, it only moves the trace on the screen. The oscilloscope is connected to the circuit being tested using a probe lead. This is a lead with a BNC plug at one end and the probe at the other. The probe lead is connected to the BNC socket on the oscilloscope for the channel being used. The probe end can be fine-pointed so that a connection can be made at any point in the circuit. The probe can also have a hook arrangement which allows the probe to be clipped to a wire in the circuit. The probe end also has a crocodile clip that is used to connect the probe to a ground reference point. Connect the probe lead to channel 2 of the oscilloscope and connect the crocodile clip to the reference point that is used for making measurements. This is commonly a ground, 0 volts point in the circuit. Before taking a measurement, a reference point needs to be determined on the screen. Adjust the Y position control of channel 2 to align the trace on the screen with the central horizontal line. This will be the reference point from which all measurements relating to voltage will be made from. The probe can now be connected to any point in the circuit, and the screen will display a waveform for that point. The channel switch should then be set to either the AC or DC position depending on the required measurements. The Timebase and Y amplifier controls can now be adjusted so that the waveform fits within the grid on the screen and readings taken. Oscilloscopes can also be used to measure DC voltages. Unlike AC signals, A DC signal has no time variation. Therefore, when a DC voltage is displayed on an oscilloscope, the traced line is displayed from its reference point by the value of the voltage. An oscilloscope can also be used to observe a changing DC voltage. For example, the charging and discharging of a capacitor can be viewed on the display screen. During charging and discharging, the trace will move up and down the screen. The voltage value can be calculated by counting the number of divisions or, if necessary, subdivisions between the reference point and the new location of the line. When this is multiplied by the amplitude scale, the voltage will be obtained. Let's now examine a waveform and interpret what is displaying. The Y amplifier is set to 1 volt per division and the time base is set to 500 microseconds per division. The center horizontal line of the screen is to be used as a reference point. First, examine the voltage. This is the vertical scale and is set using the Y amplifier control. To calculate the peak voltage, the number of divisions from the reference point to the maximum value of the voltage should be counted. In this case, from the center line to the top of the waveform is 2 divisions. Multiply this number by the Y amplifier setting, which is 1 volt per division. The peak voltage of the signal is therefore 2 volts. The peak-to-peak voltage can also be measured. This is the voltage that is covered from the minimum to the maximum of the waveform. The number of divisions covered is 4. The number of volts per division is 1. Therefore, the peak-to-peak voltage is 4 volts. The Y amplifier is set to 1 volt per division, and the time base is 500 microseconds per division. The center vertical line of the screen is to be used as a reference point. The horizontal scale is set using the Timebase control. To calculate the time period of the waveform, the number of divisions moved from one point on the waveform to exactly the same point on the next cycle should be counted. In this example, identical sections of different cycles of the waveform are exactly 2 divisions apart. Multiply the number of divisions by the Timebase setting, which is 500 microseconds per division. The time period for one cycle of the signal is therefore 1 millisecond. By knowing the time period, the frequency of the waveform can be calculated using the equation. Frequency equals 1 over time period. The frequency of this waveform using the formula is therefore 1 kHz.